So we have seen binary tree. It is a tree with two children. That is x degrees 2. So binary search tree is also a tree with degree 2. So let's draw a binary search tree. So 3 nodes you can see here. Only one you can see. Okay. So I have an element called 12 here. So I have one more element. I'm having 7 here. And I have one more element. It is 25. Okay. So you can see like this. So binary search tree, it is also a binary tree actually. That is, it is having two children only, but with a condition that we have, we can type this or set this like this is the left child. Sorry, left child. And this is the right child. Okay, and this is the root. So these are the terminologies of a tree actually. So it is the same as a binary tree or a simply tree I can say. So this is the root. In the root I am having the element 12 or data 12, and in the left child or in the left tree I am having, or in the left subtree I am having the data 7, and in the right child or in the right subtree I am having the data 25. Hope this much is clear. And we have a condition imposed on this binary tree that the right child will be having a data which is greater than the root element, and always the left child will be having a data which is um, less than the left child. Okay, so here we are having three values, 12, and you can see that 7 is always less than the root child, that is 12, and you are having a value greater than 12 at the right position. In if suppose I am inserting further values into this tree, okay, let me add a child here and add another child here, and okay, so you know, always the left child will be having lesser values than the root child. Okay, so I want to insert 22. 22 when compared to this one, it is greater. So always the right portion will be evaluated. So 25 when compared, so uh, it is less than 25. So I have to place it here, that is 22 here. And if suppose I am having 30 or 32 also there, so I need to place it here. Okay. And after all insertions, we have to check whether the property of the binary search tree is violated or not. So when I check here, 25, from the root itself we can check 12, 7 is less than 12, and 25 is greater than 12. I mean 12. Then 25 is lesser than 32, and uh, 22 is lesser than 25. Okay, so this is the condition actually. So you can see from the screen, always this property should be satisfied. Okay, so always there will be only two children, only two children. Always this binary search tree will be having two children, and these two children will be satisfying this condition. That is, always the left child will be lesser, will be having a lesser value than the root, and the right child will be having a value greater than the root. So in all the things it will be evaluated. In every deletion and in every insertion, this condition will be evaluated or checked. That is, whenever this one is there, that is always at any time this balancing or this which property, that is the property of the binary search tree, should be satisfied. Okay, so I have shown the insertion here. Now I will be deleting one node. Okay, if suppose I need to delete 25, so 12 is there, 7 is there, 25, 32, and 22 is there. So before that I will perform a search operation. So I need to find 25, then I need to delete that one. Okay, so always the start searching will be starting from the root element. Okay, so I need to search for which one I should search, the root element, and I need to search for the element 25. So that's 25, it is compared with the value given at the root element. Okay, so 12 and 25 is compared. 12 is not equal to 25. So always greater value should be searched at the right side only. Okay, so immediate right child will be checked. Okay, so 25, it is compared with the element at this position. Okay, so you can see my cursor, but I can't see here. Okay, so 25, it is compared with this position element. So we got a reply that it is matching actually. That is, I am searching for 25 and it is at this node, so it is there. So next step is to delete that one. Okay, so I need to delete this one, and we know that this 25, it is having two children, um, 20, 22 and 32 it is having, that is two children is there. Okay, so I need to uh, assign parents to this one. I am deleting 25 and I need to insert this 22 and 32 somewhere. Okay, I should not throw it away. And so this one I am deleting 25. This one I am deleting 25. I am deleting that one. So 32 is there and 22 is there. So I can move this 32 to this one. Okay, 32 can be moved to the position of 25. So it won't be violating the condition of a binary search tree. So when 32 comes here, 12 is lesser than 32, and we know that 22 is also lesser than 32. Okay, hope it is clear. That is, always when we perform an insertion or deletion, we have to check for the condition of a, condition of the binary search tree, whether it violates, that is, always the left child should be having a value lesser than the root, and the right child should be having a value greater than the root. Okay, so this is a basic idea for a binary search tree. Okay, I'll show an animation now. Before that, I'll show you an animation. Can you see this one? This screen, you can, same screen you are viewing. Okay,
Mr. Presentation boy.
1 minute. Can see, no?
Yes, miss.
So hope you can see the screen now. It is an animation actually. So here you can implement like this, like an animation or something. You can implement like this. So I am inserting a value here. Okay, so I am going to insert 32 here, and I am clicking on the button insert. So the first element, always it will be set as the root element. So it is set as the root element here. So it is clear, no? Now I am going to insert another value. So I'm going to insert 22. From the idea I have shared before, you know now that it should be placed as the left child of 32, since 32 is greater than 22. Always lesser values will be placed towards the left side of the tree. Okay, so I'm going to click the insert button, and you can see it is placed as the left child of 32. Now I am going to place 2 here. Where it will be placed? It will be placed at the left as the left child of 22 because 2 is lesser than 22. So I'm going to insert that one. Okay. Now I'm going to create another one, that is 35. I'm going to this one. So we know 32 is lesser than 35, and we know that 35 is greater than 32, and it will be placed as the right child of 32. Okay. Now I will place 33, sorry, 33. Where it will be placed? We know 32, and always when I try to insert a new element, it will be first compared with the root element. We know we have the root element 32 here, so this 33 I am going to insert. So 33 will be compared with the 32, so we know it is greater than 32, and it will be inserted here. So already we have 35 here, so it will be compared with this 35. So 35 and 33 will be compared, and we know 33 is lesser than 35, so it will be placed as the left child of 35. Okay, so I'm going to insert that one. You can see in the figure that 33 is placed as the left child. Okay, now I will be placing 34. 34 I am going to place. Where it will be placed? It will be compared here. We know that it will come at the right side only. It will be compared here. It will be it is a lesser one, so it will be comparing with 33. So we know 34 is larger or greater than 33, so it will be placed at the right side of the uh, 33. Okay, so let us see. So like that it will be placed. Okay, so I'll be trying to remove 33 now. What happens? This 34 becomes the left child of 35. So you have to bring linked list in your mind, that is this address mapping and all you have to think about. Okay, so I'll be removing 33 here. uh, I'm going to remove. Okay, so 33 is removed, and 33's child was 34, that will be connected to 35. Okay, if there is a deletion or something, there won't be any existence of any orphan records or any orphan subtrees. Okay, so hope it is clear now. And we can perform in-order, pre-order and post-order traversals as we discussed in tree traversal. So this is the in-order traversal. In-order means it is 2, 22, 32. In-order means what? A plus B. The in between we will be searching the root element. Left, root, right. That is the order in the in order. If it is pre-order means what? Always root will be visited first, then the left child, then the right child. Post order only finally only will be visiting the root at the last time only. I mean at the last chance only. Okay, so uh, root is visited at last. 32 will be visited finally. And pre-order means root will be visited first, then 22 and 2, then we have 35 and 34. Here also 35 is the root, not root. Okay, can be considered as a root. Here also 22 will be visited first, then only 2. So in all the nodes this pre-order will be followed. Okay, I'll show one more this one animation, same thing only repeating. Okay, Okay, so this is a binary search tree. Okay, so root element, then 3 is a parent, 1, 4, 6, 9 are children. Again, I can call 3 and 8 as parents. Okay, so this one, so from the figure you can see that 5, all the elements in the right subtree is always greater than the root element. We know 5, 8, 6 and 9 are greater than 5, and always the left side or the left subtree will be having values lesser than 5. Okay, so 3, 1, 4, these are values which are having lesser values than the root. Okay, um okay, this is the subtree. So in a binary search tree, each node is greater than every node in its left subtree. So you can see that if this can be considered as a subtree, 8 is always greater than 5, 2 and 6, and 15 is greater than all these values in the subtree, and always the greater values 15, um, the values will be always greater than 15 in the right tree. So each node is greater than every node in its left subtree, and each node is less than every node in its right subtree. Okay. So instructions are given, that is binary search tree insert. Always we'll be starting from the root, and we will be inserting from the leaf. Okay, so we are trying to insert 12. Okay, 12 will be comparing. So the first comparison, it is done at the root element. So 12, I'm going to insert 12 is compared with 15. So whether 12 is lesser or greater than 15, that will be evaluated, and we know that it is lesser than 15. So its left child will be compared. So that is shown in this figure, that is 12, whether it is less than 8. We know that it is not. So it will be, we will be moving to the right side, because in a binary search tree, always greater values or greater elements than the root, okay, will be placed at the right side only. So I'll be moving to this side, that is the right side. So we are comparing it here. So finally I reached here. That is, here I had an element called 13, and 13, 12 is compared with that one, and we know that 12 is less than 13, so it is placed as the left child of 13. Okay, now we are moving on to another insertion called 19. Not insertion, we are finding an element, so it will be compared with the root element, and in the next step we will be comparing the right side only. And the important thing is that our search is divided by half. That is, I need to search only half the elements. So when I know that um, the searching element will be lesser or greater. That is, when I compare with the root element, whether this element belongs to the left half or the right half. So I need to search only the right half if that particular element is greater than the right element, I mean root element. If it is less than, I need to search or move through the left side only. Okay. So 19, it is we are searching here and it was there at this position. Next is deletion. Actually, we are having three possible cases. We are like it might be a leaf node. It may be having one child or two children. These are the three possible cases for deletion. Okay, either the the node I am going to delete may be a leaf node, or it may be uh, a node which is having a child, or it may be a node which is having two children. Okay, for example, if this is the case, or if 2, 6, 12, or 25 is the case, it is the leaf node. Just we need to release that node, that's all. And if 11 or 13 or 28 is the case, it is having one child each. Okay, and if I am deleting 5, 24, like that, they are having two children. Okay,